So now that we've kind of know how we come up with these estimators through minimizing that sum of squares, we can talk about interpretation, right? So interpretation of our multiple regression. Here it's going to be kind of a little bit more clear why we had that extra sentence holding everything else constant when we first introduced multiple regression. So after we run the regression, we have y hat here, which is equal to beta hat 0 plus beta hat 1 x1 plus beta hat 2 x2 plus however many more we have. But let's just assume that we have just two x's right now. So assuming k equals 2 here, just so we don't have to write a whole bunch of things. So let's start interpreting beta 0, beta 1, and beta 2, all of them hats, right? The actually estimated amounts here. So beta hat 0 is going to be the predicted value of y when x1 equals 0 and x2 equals 0. So just like before, this can be interesting and important. In some cases, other times not. So sometimes our intercept, and we saw this with simple regression, sometimes it's meaningful, it kind of says something interesting to us, and then sometimes it kind of doesn't, right? So this is the same in multiple regression, but basically, if we make x1 equals 0 and x1 equals 0 and x2 equals 0, then the intercept is our predicted value of y. So that's the idea with beta hat 0. Now we can start talking about beta hat 1 and beta hat 2 and thinking about these as kind of partial effects. And we'll see to get the real effect of, to isolate the effect of x1 on y, we'll have to shut down x2. But we'll see that in 1 second. So now moving on to beta hat 1 and beta hat 2. Beta hat 2, these are partial effects. So we know that the change in y hat is going to be equal to beta 1 hat times the change in x1 plus beta hat 2 times the change in x2. And so if we kind of want to interpret beta hat 1 in terms of how it affects y or predicted level of y, we kind of have to shut down this second term on the right hand side. So let's write that out. So if the change in x2 equals 0, maybe I'll do an arrow here, then the change in y hat equals beta hat 1 times the change in x1, and the same thing the other way, where if the change in x1 equals 0, so if this equals 0, then beta 2 is capturing the change in y hat over the change in x2. So this is kind of why when we originally kind of introduced multiple regression, we had that second part that was holding the other thing constant. So let's do a quick example with numbers and we can interpret it just like we did in simple regression. So let's do a quick example of interpretation just so we can kind of see how to interpret things when we're given kind of actual numbers. It's going to be very similar to what we saw in simple regression, but let's just go through it to make sure we're all on the same page. So let's say, again, k equals 2, so we're going to have two independent variables, but our dependent variable is college or university GPA. and this is going to be a 4-point scale. Let's say our first independent variable is high school GPA. Again, this is going to be a 4-point scale. So 1 unit change is a pretty big change here, right? And X2 is going to be the ACT score. So that's just a standardized test in the States, just like the SAT is kind of similar in that respect. Okay, so the first thing we should think about, or let's write out our regression, I guess, is the first thing that we should do. So we have this data, we enter it, we load it into Stata, we run this regression with these two independent variables, and we get these results. And then plus 0.0, maybe we'll put a 0 so it's clear, 0.0094 ACT. So let's say we run this. This is the results we get after we run our regression in Stata. Kind of write it out. So the intercept is 1.29. Well, is this intercept really meaningful here? It's probably not meaningful, right? If you had remember the intercept is the predicted college GPA when high school GPA and ACT scores are 0. Now, how many individuals probably have a college GPA if they had a 0 high school GPA and a 0 score on their standardized entrance exam? Probably not many, right? So it's not very meaningful here. So let's write out the interpretation, but then let's make sure we note that it's not meaningful. Predicted college GPA of an individual with an ACT and high school GPA of 0 is 1.29. And again, I'm just going to note that it's not meaningful. Just because we don't really have anybody, probably there's not many individuals that have those characteristics, right? So it's not very meaningful here, but let's turn our attention to the two slope parameters here. All right, so I've rewritten our results just higher up. We've already interpreted this intercept, the beta hat 0, so let's turn our attention to beta hat 1, which is this number right here. So what this means is holding ACT fixed, so we need to, remember we're holding this fixed so that change in x2 equals 0. Holding ACT fixed. A 1 point increase in high school GPA is associated or is predicted to increase college GPA by 0.453. Okay, again, this is a big change, right? Like if it's a 4-point scale, a 1-point increase in high school GPA is a big difference. Like the difference between a 3.0 and a 4.0 is significant, right? And just the same for college GPA here. Now we can do beta hat 2, so the coefficient on ACT, I'm just going to multiply it by 10, so instead of looking at a 1-point change in ACT, I can do a 10-point change, just to make the number a little bit bigger, but you can interpret it just a 1-point change as well. A change or an increase in ACT scores by 10 points, or 10, is predicted to increase college GPA by less than a tenth of a point. And again, we need holding high school GPA fixed. So again, we have to hold the change in x1 equal to 0 like we just learned. So that's what this last part is about. Holding this constant 10 unit increase or 10 point increase in ACT. So this 0.094 is going to be the increase in the college GPA that's predicted by this model.